today will
nothing shady happening there. Who dictates that? It some that if it is accepted, then puzzle A to puzzle B or proposal, and I think or probably switched completely. So the code changed. So people can propose a new change, but BTC has been working for many years. Doesn't make too much sense to change it. It is what it is, and it does solve a very bad puzzle, but it's just accepted, and no one's proposing an improvement on it. And if they are, it's not getting accepted. And the same might be true for Solana and kal ko kuch aur, some other blockchain might come that might solve something better, and Solana might not move to that because they have their own reasons not to. The same is true for Ethereum could have done 10 things to make it faster, but it didn't. And Solana ended up doing those things, and Ethereum had its reasons not to move to those new code bases, those new whatever algorithms, those new architectures. So you can propose, but the voters or people can decide whether or not to introduce that proposal. All right, it's 11:40. It's a long class. We'll try to stick to 2-hour classes from now on. But hopefully it was an interesting class. Hopefully you learned something new. And I'll see you guys next week when we get a little more into, creating wallets, receiving balances, updating balances, DevNet, so on and so forth. I'll see you guys next week, folks. Have a good night. Bye-bye.
So basically the lecture or the session today we'll be talking about the whole course of AI, of how it started, when it stopped in between, there was some time, and then what happened before we discovered transformers, and what was stuff before it, because we directly didn't end up on coming to transformer, but usse pehle bhi, I think we have a lot of sequence model like RNNs. Before that we have statistical models, and before that I think the most basic things were rule-based model. So before I start this, I think we all should start from this very first question, which is, okay, I cannot, yeah. What does it mean to learn? I think I should open chat for this. Okay, my screen is stuck, guys, sorry. Yeah, what does it mean to learn? I'll open the chat and I'll look at some answers so we can move a bit intuitively. Can you guys mention what does it mean to learn? I don't see any messages here. Yeah, basically right. Understanding patterns. I think if we look at our lives, if we had to learn how to ride a bicycle, we first have to experience it. I think we might fail a couple of times, but the final thing would be we might end up learning something. So it's basically changing ourselves based on some experiences. Like we try something, then we change according to it. like how does I move, how should I push the pedals, and how should I control the handle, and all of these things. If we are talking about bicycle, but this can be applied into all of the things we ever learned or we are going to learn in future. This is the basic concept of learning, and from these very basic concepts, we'll get onto the more, I think, niche topics like machine learning, artificial intelligence, deep learning. But when you look at it and you go back to these same questions, you'll able to understand that these are very fundamental things that we just somehow programmerize, and yeah, it looks good. So basically, yeah, learning is a loop. We try something and then see what happens. Imagine you are learning to ride a bicycle. You try riding it first, you might fall off. You see, oh, I fell off. That's a feedback. So you are getting something in back in the reaction from the action you are doing. So it's like you are getting a response, which is, I think you all might have done or heard this in physics that for every action we have a equal reaction. This applies here too. If we are doing something, we are getting an answer or a response in as a feedback from it. Based on that feedback, we adjust ourselves or our habit or anything. It can be literally anything. Based on the feedback, we change it. And if we do it for, I think, long enough time, we'll be able to, in case of bicycle, understand or learn how to ride a bicycle. If we are talking about learning machine learning, if we do the same thing and apply the same learning loop over there, we'll end up learning some part of machine learning which we are focusing on and getting a straight feedback from. So this is the whole concept of learning. You learn basically experiencing, then getting a feedback, adjusting yourself, and then repeat karna. This is very simple. I assume you guys might be able to understand it. Give me a thumbs up in the chat and we'll continue. Sounds good. Okay. Yeah, thanks for the poll. Sounds good. How do I get rid of this poll? Yeah. Then comes the next question. What is knowledge? What does it mean to know? Again, the same thing. Knowledge is basically you get information of something, and there's two type of knowledge. One is explicit knowledge, one is implicit knowledge. Explicit knowledge is, yeah, it's something which you learn from rules. So if I say that the capital of India is Delhi, that's explicit knowledge because we have a defined rule, or you can say fact for it, because we can say that and it is not wrong. The capital of India is Delhi. This is known as explicit knowledge. Implicit knowledge is completely opposite. Like if I ask you, how do you remember the face of your friend? You might not have a direct answer for it or a set of rules which you can say, like, okay, his face shape is this, his eye shape is this, but you cannot be very definitive of it. It is something you learned from experience, or something in your brain changed, some patterns matched, and that whenever you see your friend that okay, he's my friend because some pattern matched and you can recognize him correctly. So these are basically two types of knowledge: explicit knowledge and implicit knowledge. Based on this, we'll build some concepts later. Now comes the, I think, greatest question in philosophy, in I think human, mankind, whatever. What is intelligence? Intelligence, I definitely some pattern matched and you can recognize him correctly. So these are basically two types of knowledge: explicit knowledge and implicit knowledge. Based on this, we'll build some concepts later. Now comes the, I think, greatest question in philosophy, in, I think, human, mankind, whatever. What is intelligence? Intelligence, definitely there's no, I would say, an exact definition for what intelligence is. There's
if this was just pattern matching, then it wouldn't make any sense. It has to be more than intelligence. What intelligence means, maybe like performing.
a lot of debate going on in this, but it's basically an ability to, perform good in a very wide range of activities or situations. Like if I give you an example of calculator, it is very good at solving arithmetic questions, but do you call it an intelligent device? Yeah, we do not call it an intelligent device because it is just good at a very particular skill, but in all the other skills, it's not, like, it cannot even perform any basic things. But if we talk about us humans, what's different there? We can learn some sort of arithmetic, we can learn some sort of development or DSA, and then we can say calculus on all of that. So we have a very wide range of, catalog to learn from, and ability to achieve or ability to learn these wide range of things, I would say, is intelligence. So this is the whole idea of intelligence. Now, what is AI? AI is artificial intelligence. We want to somehow make this the, I've already defined what intelligence is. So basically, we somehow want to transform this in a way that computers can understand or can be intelligent. So they can also be good at a wide range of tasks and not just particular stuff which rules can be defined for, but very general stuff like making good jokes, understanding sarcasm, answering your basic questions. It can be, yeah, any questions, like you can chat about literally anything now with ChatGPT. So that was the idea of artificial intelligence. Like, how do we make that happen? Now let's get to the goal. The ultimate goal is artificial intelligence, and in there comes machine learning, and in there comes deep learning. So these are the subsets of AI. Basically, what AI is, I've already talked about it. making machines intelligent to do something like humans. It can be recognizing faces, playing chess, driving a car, understanding the language. But you can see it's a very wide range of catalog and not just a particular thing. So, as we already talked about, what was the first thing, or what is the first thing that would come to mind of, you can say, people living in 1950s, 1960s, if they want to make machines intelligent? I think the first thing that can happen is, writing rules for stuff. As we defined explicit knowledge, like the capital of India is Delhi. So we can write these set of different rules. Like if an email contains some specific keywords, you can list it as spam or important. If the temperature is above a certain degree of Celsius or Fahrenheit, you can consider that as a fever or hot or cold. If a chess piece moves a square, and how does a rook moves, how does a horse moves, and all of that, we call these rule-based systems. So this was the first attempt in making artificial intelligence or making machines learn. So do we get that? Let me open up chats. Great. Yeah, I think we understand what the first thing we did in AI. So that was the literally the first thing any human can think, or you can literally ask anyone like, how do you make machine intelligent? We'll say like, let's write 100 rules for something, and if that system follows that rule, we can basically call it intelligent in the field for which we have made the rules of. So it kind of gives a sense of making something intelligent, but is it really intelligence? Like, does our machine really understand what this specific keywords are, and why do these specific keywords make an email spam or make an email important? No, right? So this was not the ultimate goal, or this was not the oracle of AI. So yeah, research continued, a lot of stuff happened. So we've already discussed the rules and what are the problem with it. Like if I ask it to understand a sarcasm or understand a joke, it cannot, because we have simply listed rules for what is good, what is bad, what is spam, and what not. So it would not be able to understand any contextual meaning of the sentence or anything you write. It would not be able to recognize face, because let's say you build a face recognition system based on rules. The max you can do is that the length of the eyeball is this, he wears specs, the hair, the shape of the hair, and all of that. But in सबके बाद भी we cannot literally make a system just based on rules which will be able to recognize a face. That is completely out of it is complete and impossible situation in this case. Yeah, it is complete and impossible situation.
This is why everybody loves.
to talk a little bit about reinforcement learning. So, people talk about neural networks and loss, and they talk about how you have a language model that's maybe predicting next tokens, and that's all well and good, but that sort of paradigm isn't going to get you models, AIs that can take actions in the real world. And I'm going to talk a little bit about why, and I'm going to talk about how we fix it. First, let's look at a setup, little toy example where we'll try and solve the problem using just standard gradient descent, and then we'll talk about why that doesn't work. Let's say that you want to train a neural network to play chess. Okay, kind of normal thing to want to do. A thing you might try to do is go, okay, well, I'm going to have a loss function. Loss is the fancy term we use to mean how good or bad a job our AI is doing at a task. And we could say, all right, plan. The loss function is going to be, did it win the game of chess? And I'll just put it up on chess.com and have it play lots and lots of people, and it'll learn to win the game. The way that gradient descent works is we need to be able to train. We're going to talk a little bit about reinforcement learning. So people talk about neural networks and loss, and they talk about how you have a language model that's maybe predicting next tokens, and that's all well and good, but that sort of paradigm isn't going to get you models, AIs that can take actions in the real world. And I'm going to talk a little bit about why, and I'm going to talk about how we fix it.
The fuck?
First, let's look at a setup, little toy example where we'll try and solve the problem using just standard gradient descent, and then we'll talk about why that doesn't work. Let's say that you want to train a neural network to play chess. Okay, kind of normal thing to want to do. A thing you might try to do is go, okay, well, I'm going to have a loss function. Loss is the fancy term we use to mean how good or bad a job our AI is doing at a task. And we could say, all right, the loss function is going to be, did it win the game of chess? And I'll just put it up on chess.com and have it play lots and lots of people, and it'll learn to win the game. The way that gradient descent works is we need to be able to take a gradient. We go, well, if I change my AI a little bit this way or a little bit that way, tweak the parameters, would it make me get better or would it make me get worse?
So here the aim of the game is to be at the top of the curve, would that be right? Or as high as you can?
Traditionally, we say the bottom of the curve,
Okay.
But negative signs, tomato, tomato, top of the curve.
Okay, so let's say bottom of the curve. Actually.
Yeah.
Let's go with the norm.
So we've got, this gradient we want to take, this thing that tells us, well, if I make a little tweak, take a little step this way or a little step that way, do I go up or down? dy dx. How much does a little change in x affect y? We might want to write this as the derivative of loss, how good or bad our model is when we make a little change, so derivative to our parameters.
Oh no, we're going all number file now. Go on. I'm hanging in there for now.
It's a Greek symbol, but the parameters, the way that our network is shaped. The only problem is some things are nicely differentiable. Some things it's really easy to see how changing my model would change the outputs. If I want my model to learn to replicate someone else's actions, I can go, well, they'd be more similar to that person's actions if we changed it in this way, and it'd be less similar if we changed it in this way. But whether or not I win a chess game isn't really something I know how to take a derivative of. They didn't teach me this in calculus class because there's not a function for whether or not I won the chess game. My opponent thought, with their brain and made some other moves, and then I made some moves and my opponent made some moves, and like eventually I won or lost the chess game. And if I'd made a move a little bit differently, I don't know what would have happened. My opponent could have done something totally different. So we can't take a gradient. We just don't know how changing our network, our AI, would change the outcomes. And we see this for most real world tasks, right? Most things you can't have a nice little function for. Throwing and catching a ball. Like, I sort of know the laws of physics, but man, I don't know what the wind was like or whatever. I don't know how it would have gone differently if I'd done something different. Trying to, like, sell things, and you want to make money off of the things you're selling. Writing code that, like, accomplishes a task and seeing if the code passed the, like, unit tests. These things aren't differentiable. You could try and make
way down a dark mountain. You can't see where you're going, so you have to feel your way around. You take small steps in the direction that feels the most downhill. Eventually, if you keep going, you'll find your way to the bottom. That's gradient descent. Let's get into it. So gradient descent is a common optimization algorithm used to train machine learning models and neural networks. By training on data, these models can learn over time, and because they're learning over time, they can improve their accuracy. Now, you see, a neural network consists of connected neurons like this, and those neurons are in layers, and those layers have weights and biases, which describe how we navigate through this network. We provide the neural network with labeled training data to determine what we should set these weights and biases to figure something out. So, like, for example, like this, and those neurons are in layers, and those layers have weights and biases, which describe how we navigate through this network. We provide the neural network with labeled training data to determine what we should set these weights and biases to figure something out. So, like, for example, I could input a shape, the neural network in layers, and those layers have weights and biases, which describe how we navigate through this network. We provide the neural network with labeled training data to determine weights and biases. Biases, which describe how we navigate through this network. We provide the neural network with labeled training data to determine what we should set these weights and biases to figure something out. So, like, for example, I could input a shape, let's say like that, and then we can use the neural network to learn that that squiggle as our input represents as output the number 3. After we train the neural network, we can provide it with more labeled data, like this squiggle, and then we can see if it could also correctly resolve that squiggle to the number 6. If it gets some of these squiggles wrong, the weights and biases here can be adjusted, and then we just try again. Now, how can gradient descent help us here? Well, gradient descent is used to find the minimum of something called a cost function. So what is cost function? Well, it's a function that tells us how far off our predictions are from the actual values. So the idea is that we want to minimize this cost function to get the best predictions. Now, to do do this, we take small steps in the direction that reduces the cost function the most. If we think about this on a graph, we start here, and we keep going downhill, reducing our cost function as we go. The size of the steps that we take, so the size of the steps from here to here and to here, that's called the learning rate. Let's think about another example. Let's consider a neural network that, instead of dealing with squiggles, predicts how much a house will sell for. So first we train the network on a labeled data set. Let's say that data has some information like the location of the house, let's say the size of the house, and then how much it sold for. So with that, we can then use our model to train new labeled data. So here's another example. We've got a house, its location, let's do it by zip code, 27513. How big is it? 3,000 square feet. Input that into our neural network. So how much does this house sell for? Well, now our neural network will make a forecast. It says, we think this sold for $300,000. And we compare that to the forecast of the actual sale price, which was $450,000. Not a good guess. We have a large cost function. Weights and biases now need to be adjusted, and then the model can try again. And did it do any better over the entire labeled data set, or did it do worse? That's what gradient descent can help us with. Now, there are 3 types of gradient descent learning algorithms, and let's take a look at some of those. So first of all, we've got a gradient descent called batch. This sums the entries for each point in a training set, updating the model only after all the training examples have been evaluated, hence the term batch. Now, in terms of how well does this do? Well, computationally, it is computationally effective. You can give this a high rating because we're doing things in one big batch. But what about processing time? Well, with processing time, we can end up with long processing times using batch gradient descent because, well, we've got large training data sets and it needs to store all of that data in memory and process it. So that's batch. Another option is stochastic gradient descent, and this evaluates each training example, but one at a time instead of in a batch. Since you only need to hold one training example, they're easy to store in memory and get individual responses much faster. So in terms of speed, that's fast, but in terms of computational efficiency, that's lower. Now, there is a happy medium, and that is called mini batch. And mini batch gradient descent splits the training data set into small batch sizes and performs updates on each of those batches. That is a nice balance of computational efficiency and of speed. Now, gradient descent does come with its own challenges. So for example, it can struggle to find the global minimum in non-convex problems. This was a nice convex problem with a clearly defined bottom. So when the slope of the cost function is close to 0 or it's at 0, the model stops learning. But if we don't have this convex model here, but we have something like this shape, that's known as a saddle point, and it can mislead the gradient descent because it thinks it's at the bottom before it really is. This is going to keep going down further. Called a saddle shape because it kind of looks like a
maybe copy things. So maybe I look at like Magnus Carlsen or someone who's great.
Situation in this case.
Horse saddle, I guess. Another challenge is that in deeper neural learning networks, gradient descent can suffer from vanishing gradients or exploding gradients. So vanishing gradients are when the gradient is too small and the earlier layers in the network learn more slowly than the later layers as we go through this network here. Exploding gradients, on the other hand, are when the gradient is too large and that can create an unstable model. But look, despite those challenges, gradient descent is a powerful optimization algorithm, and it is commonly used to train machine learning models and neural networks today. It's a clever way to get you back down that mountain safely.
Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have two main goals for this video. The first is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more into how this particular network performs, and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer, plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked.
Great at chess. Whether or not I win a chess game isn't really something I know how to take a derivative of. They didn't teach me this in calculus class, because there's not a function for whether or not I won the chess game. My opponent thought with their brain and made some other moves, and then I made some moves and my opponent made some moves, and eventually I won or lost the chess game. And if I'd made a move a little bit differently, I don't know what would have happened. My opponent could have done something totally different. So we can't take a gradient. We just don't know how changing our network, our AI, would change the outcomes. And we see this for most real world tasks, right? Most things you can't have a nice little function for. Throwing and catching a ball. I sort of know the laws of physics, but man, I don't know what the wind was like or whatever. I don't know how it would have gone differently if I'd done something different. Trying to sell things, and you want to make money off of the things you're selling. Writing code that accomplishes a task for someone who's great at chess. And I go, well, in this situation, here's the move that someone who's great at chess did. And now I have something that's differentiable, right? I can see how similar what I did is to what they did, or what my neural network did is to what they did. And I go, well, maybe if it had put a bit more probability on moving the knight, that would have been more similar to what Magnus Carlsen did, because he moved the knight. But that's got a lot of problems with it. For one thing, you're not going to get better than Magnus Carlsen. For another thing, Magnus Carlsen doesn't play that many games. Surely if you can just play lots of chess games, you should be able to learn something from every one of those. So instead, we're going to take these things that aren't differentiable, and we are going to make them differentiable. We're going to learn what these functions are. I don't know right now how to predict whether or not a certain chess move will lead to winning or losing a game. But that is something that I can learn with another neural network. Well, really just kind of one hammer, and computer scientists have these days, and we hit everything with it. So, predicting things, that I can take a gradient on, right? I can look at a bunch of chess games, and I can go, okay, well, I see that I don't know how to draw a queen. The queen is here, and the king is there, and that doesn't look like a good position. Probably they're gonna lose. The probability they win is very small probability. Great, I can train a neural network to make this prediction. And this is differentiable because I can go, well, the real answer is they won or they lost. And if the neural network had come up with a higher number, that would have been closer to 1 if they won, and farther from 0. It's very easy to see how little tweaks to the output of my neural network change its accuracy. We know exactly what kind of output we're looking for, and we can just go, yeah, well, what's the difference, right? The difference, take that as our loss, easy peasy. So a thing we can do is we can learn a reward model, learn what it looks like to make a good chess move, what it looks like to move your hand in a way that's likely to catch the ball. And once we have our reward model, that is a neural network. That is differentiable. It's, a whole pile of math. It's a lot of layers of math. It's a lot of little equations, activation functions, but I can take a gradient through that, right? I know how to do the output of my reward model changing as my model changes. We've got two AIs now. We want to have different names for them to keep them straight. So we call the one that's telling me if I'm doing a good job the reward model, and we call the other one the policy. So as I change my policy, how does my reward model change? And that tells me, probably whether I'm doing a good job or not. And then I can look at that and I can learn how to improve my policy. That's one frame on RL. People use a lot of different frames, but it's one that I particularly like, at least in this sort of deep learning era. I should note, sometimes you're not going to learn the reward model as explicitly. Sometimes you're going to learn something else, like how good an action looked, rather than how much reward you'll get at the end of the day. But this is the general shape of when you need RL and how RL is trying to solve these problems. Now, there's a couple of things I want to talk about with how this connects to the real world. So language models are first trained to be next token predictors. We have a lot of internet text. They are trained to predict what the next word's going to be in a passage. And this gets you something that's called a base model. I don't know if you maybe try talking to a base model sometime. It's a bit of a painful experience because being able to say the next word of internet text is not always that useful. That's not what I was really looking for. So you've got your base model and you want to turn it into something you can talk to. One thing is you could take a bunch of very smart humans and have them write, I don't know if you maybe try talking to a base model sometime, predict what the next word's going to be. In a passage. And this gets you something that's called a base model. I don't know if you maybe try talking to a base model sometime. It's a bit of a painful experience because being able to say the next word of internet text is not always that useful. That's not what I was really looking for. So you've got your base model and you want to turn it into something you can talk to. One thing is you could take a bunch of very smart humans and have them write like very good, poised text and train it to imitate those humans. But there's a couple problems here. One problem is that's very expensive. You need to get a lot of humans to write a lot of text. Another problem is that's only going to get you text that is as good as the humans you can find. I want models that can make text I couldn't even write. And certainly text that's better than what I can, hire 1,000 MTurkers to write. So we can train a reward model. We can do what's called RLHF, reinforcement learning, with human feedback. We get a bunch of humans and we show them, say, like 2 different things our language model wrote, and the humans pick which one they like better. And we train a different model to predict which ones the humans will like better. Reward model. And then once we have this reward model that can predict what the humans would like, now we can train our language model. And this is one of the techniques they use to go from GPT-3 to ChatGPT. I want to not overstate this too much. I think that there's a lot of other things that went into that. I think it's plausible simply fine-tuning, which is the word for like imitating those experts who are good at writing things and could have gotten us there. There's also a lot of other techniques people use, like, what if we just have the model? We have these models now. What if we have them do the rating and try and work something out of that? And there's a very clever thing called DPO that people do. But this is the broad thrust of it. Now, RL doesn't solve all our problems. For one thing, your model is only as good as the reward function that you're using.